Welcome to this explainer. Today we're doing something really hands-on. We are going to transform abstract geometry into a tactile master builder's guide using only the purest tools. We aren't just passively looking at shapes today. We're actually figuring out the ancient art of constructing them totally from scratch, turning raw measurements into undeniable visual truths.
So here is the structural blueprint we'll be following today. First, the master builder's tools. Second, constructing basic quadrilaterals. Third, the parallelogram puzzle. Fourth, perfect rectangles and rhombuses. And finally, number 5, the elegant regular hexagon. Now, before we lay down our very first foundational line, we absolutely must define the strict rules of our universe, which come directly from our source material. We have a massive absolute constraint here. No protractors allowed. None. We're using just a ruler for our straight lines and a compass for our arcs and distances. And that's literally it. It's almost hilariously strict, like being asked to build a whole house without any power tools. But honestly, this limitation is exactly what makes this whole process so fascinating. It forces us to rely entirely on the pure logic of geometry, rather than just lazy reading degrees off a cheap plastic semicircle.
All right, let's jump into Section 1, the Master Builder's Tools.
What's really fascinating here is that the source text explicitly commands us to always sketch a rough vision first, just like the one shown for quadrilateral ABCD. It seems super simple, right? But before we commit to the math, the strict scale, and the precise swings of the compass, we desperately need a spatial map. It's essentially the golden rule of construction: visualize before you materialize. This little hand-drawn sketch acts as our anchor to make sure our final geometric reality actually makes sense.
Think of your given measurements as your ingredients. Notice how differing constraints drastically change the recipe. If we're given 4 sides in one angle, our approach is vastly different than if we're handed a puzzle made up of 3 sides and 2 intersecting diagonals. Depending on exactly what measurements you're handed, your step-by-step drafting strategy changes completely. You really have to adapt your tools to the exact data you have.
Let's move on to Section 2, constructing basic quadrilaterals. So we're turning abstract data into physical boundaries here. The source text outlines a very specific procedural rhythm for this. First, you drop your baseline to give yourself a solid floor. Next, you construct your exact angle originating from that base. Then, using active, dynamic strokes, you swing your compass to cut specific lengths along those lines. And finally, you find that absolute perfect intersection point hanging out in the empty space for your final vertex.
And this brilliantly illustrates our recipe in action. Looking at this construction straight from the text, you can literally see the visible evidence of our tools. Those compass marks, those little crossed arcs up at point D, they lock those specific lengths and the 45-degree angle into a permanent structure. Point D isn't just eyeballed, right? It is definitively summoned exactly where the 4-centimeter and 5-centimeter arcs collide.
Okay, on to Section 3, the parallelogram puzzle.
Now, here's a absolutely crucial geometric truth. The diagonals of a parallelogram inherently cut each other exactly in half, and knowing this unlocks a massive shortcut for us. Let's say we're tasked with building a parallelogram when we only know the length of one side and both diagonals. Well, because of this bisection rule, we can easily locate our center point O without measuring the outer walls first. We literally get to build the shape from the inside out, starting with a central triangle and just projecting everything outwards. But the text wisely warns us about some real-world physical limitations. It brings up what we can call the 2.25 centimeter dilemma. Think about it. If you have a diagonal that's 4.5 centimeters long and you need to bisect it, its exact half is 2.25 centimeters. But look at your standard geometry box scale. It is going to completely fail you here. You just cannot measure down to 1/4 of a millimeter accurately by eye. So, to overcome this, you must strategically start your construction with the other diagonal instead, the one that divides cleanly, so you don't instantly compromise your structural integrity right out of the gate. Moving from parallelograms, we encounter the trapezium. A trapezium requires exactly one pair of parallel sides. Now, to construct this without cheating and using a protractor, we actually have to draft parallel lines using perpendiculars. To make the top line parallel to the base, you have to construct a perpendicular height and then draft another perpendicular line shooting right off of that to create a perfectly flat roof. It's essentially multi-step paper engineering. Which brings us to Section 4, perfect rectangles and rhombuses.
Adding these strict rules forces us to step back and ask a really critical question about symmetry in our tools. What exactly happens to our construction steps when the diagonals cross at exactly 90 degrees? How does that alter our whole blueprint? It's honestly amazing to see this architectural shift side by side.
A rectangle forces 90-degree corners, which means you spend your initial effort constructing right-angled triangles right at the baseline vertices. But the rhombus? Well, that demands a perpendicular bisector straight through its heart. Because the diagonals of a rhombus bisect each other at perfect right angles, you establish a perfectly square crosshair right in the absolute center of the page first. Cut your diagonal lengths from that origin, and simply connect the outer dots.
All right, finally, Section 5, the elegant regular hexagon.
Our source material actually gives us 3 completely distinct, elegant methods to summon a regular hexagon, and each one relies on a different geometric truth. Method 1 leans on the fact that every interior angle is exactly 120 degrees. Method 2 utilizes the amazing relationship between the hexagon's side length and its circumcircle radius. And Method 3 builds from the center outwards, using 60-degree subtended angles. Having 3 totally different ways to solve one problem, now that is the hallmark of a true master builder.
But notice the stark difference in the drafting approach here between Method 1 and Method 2. Method 1 carefully builds those 120-degree angles point by point around the perimeter. It's sturdy, sure, but mathematically laborious. Meanwhile, Method 2 is just an absolute masterclass in visual flow. It elegantly traces a perfect circle and effortlessly slices it into 6 equal parts.
The sheer elegance of Method 2 is what we call the circumcircle secret. The real magic trick here is that the radius of the outer circle is perfectly identical to the side of the hexagon itself. Because of this, once you draw your initial circle, you never even have to adjust your compass again. You just lock it in, place the needle on the edge, and literally walk your compass step by step around the circumference, making little cuts. Those cuts automatically find all 6 vertices with flawless precision. It's brilliant.
So after mastering these specific recipes, the source text decides to push us out of the nest. It challenges us with complex, multi-layered puzzles in the Test Yourself section. These are specifically labeled as Applying Higher-Order Thinking Skills, or HOTS. They demand that we drop the easy hand-holding step-by-steps and blend all the disjointed techniques we've just covered together into a single, cohesive architectural solution.
And on that note, I'm going to leave you with this provocative higher-order thinking puzzle straight from the source text. How would you begin to draft this highly constrained trapezium using only your ruler and compass? You know the height between the parallels is 3.3 centimeters, the base is 4.5, one angle is exactly 120 degrees, and the other is definitively obtuse. Think about the invisible structural lines, the perpendiculars, and the logical flow required to build this completely from scratch. What is your very first compass swing going to be?